Hello AP Chemistry students. This video will go through the most fundamental terms that we often find in Chapter 2 collegiate chemistry textbooks. We want to make sure we have a firm understanding of these terms because we will be utilizing them throughout the rest of the course. To dig in first, the atom. An atom is often defined as the basic building block of matter. We know that an atom is made of protons and neutrons found in an extraordinarily tiny, dense nucleus surrounded by electrons. Well, it's only when you put atoms together that you get our amazing world, that we get matter. If you put a bunch of protons together, you don't get anything. A bunch of neutrons, you don't get anything. But when you put atoms together, that's how we get our extraordinary world. An element is a specific type of atom. So an atom is quite generic, just like the term student. But then we can have individual students like Jane Smith and John Dalton, Marie Curie. Those are specific individuals. So an atom is like student, where an element is the specific student. So if we're talking about hydrogen, that is an element, and we can have atoms of hydrogen, atoms of iron, atoms of gold. Now these are all building blocks of matter, but they are different in their identities. And we'll talk about, what makes definitely an element in just a moment. Compounds are two or more atoms chemically combined. They are chemically bonded. Remember, elements and compounds are pure substances. They cannot be physically separated. An atom is just a little generic, so we could say atoms and compounds are pure substances, but at our level, we're talking about specific atoms. So that's why usually we talk about the two types of pure substances, we divide it into elements and then compounds. All right, so next, what gives an element its identity? Well, that would be the atomic number. The atomic number is the number of protons that are found within the nuclei of an atom. It does not matter the number of neutrons or electrons toward identity, simply the atomic number. And the atomic number, of course, are the whole numbers that we find in the element block within the periodic table. So what makes oxygen oxygen is it has 8 protons, or an atomic number of 8. What makes bromine bromine is it has 35 protons, or an atomic number of 35. Sometimes your textbook can refer to atomic number and different textbook, different authors, different chemists, with a capital Z. Now, mass number. We need to make sure that, we know the specific differences between mass number, average atomic mass, and then often we use the term atomic weight. All right, if we would take the element silicon. Silicon has the element symbol of Si. The average atomic mass, that is the correct terminology. That is if we take the number that is not the whole number in the element block, and if we round that to the 100th place. And that is the appropriate way that we will address average atomic masses. Now, for right now, this has a unit of AMU, atomic mass unit. We'll talk about that much more in Chapter 3, or the first unit that we'll tackle when we're all together. Now, usually we are using gram because it's talking about mass, and that's how we practically express average atomic masses. But it is not erroneous to label this with an AMU. Then we're talking about individual atoms of the element. Gram, we'd be talking about a mole of that element. But the point we want to make, average atomic mass. the value that's appropriate is the rounded value to the 100th place that we would get from the periodic table. So then what if we drop that term average and just call it atomic mass or mass number? Well, then we should just report, for example, silicon to the whole number. The whole number. This, in essence, or in a very elementary approach, we say is the number of protons and neutrons that we find within our element where we've attributed a single proton and a single neutron to be the AMU value of 1. All right, so what we can do if we know the mass number or atomic mass. Now again, that means we've rounded to a whole number and we're not reporting it to the 100th and we're not using the term average. Well, then we can actually use this to help tell us different things about our element. Now, what makes silicon silicon is the atomic number is 14. That means there's 14 protons. Now, if we would have 15 protons, it would be phosphorus. 13, it would be aluminum. The number of protons gives us our identity. All right. Well, if the mass number is 28, and this is protons and neutrons, then subtracting 28 and 14 gives us the number of neutrons. Again, to get the number of neutrons, that would be mass number, which is protons and neutrons. And if we subtract from that the atomic number, which is the number of protons, then we'll get the number of neutrons. Now we know every proton is assigned a positive value of 1, and every electron is assigned a negative 1. Well, if this is silicon, if I am just calling it that, then it must be neutral. And to be neutral, we have the same number we know of protons and electrons. Now, it's not that the number of electrons is equal to atomic number. Here we know it's a neutral atom, and so then to be neutral, we need 14 electrons, and we know we have 14 protons because of the atomic number of silicon. Now, what if this were an ion? How would we know? Well, we would either say this is silicide. So remember, we drop the ending and replace with "ide" if it's an anion. And we would show it with its negative charge. So if there is not a charge, then you know hands down it is not an ion. This is an anion, which you know are negative ions. This would have, it's silicon, 14 protons. Now, to be an ion, that does not mean that the mass has changed. And the mass comes from the nuclei. The electrons, remember, are so insignificant that they do attribute mass, but it's to the 1,000th place compared to the protons and neutrons, so we ignore it. So if we're going with this as our mass number, then it'll still have 14 neutrons. But how did we get to be -4? We have 4 more electrons beyond what would make us neutral. So this would have 18 electrons. Now, what if we would have a cation? So let's say, let's deal with chromium +3. How's that? All right. Now, to be chromium, we have to respect the atomic number to get the number of protons, which would be 24. Now, the mass number, I would round this to 52. That's my protons and neutrons. So subtracting 24. So 28 neutrons. Now, a positive is created, a positive ion, because we lost electrons. We lost 3 electrons compared to the number of protons. So this would have 21 electrons. All right. Now, why do we call this an average? Because it takes into account the isotopes of every element, which we'll get to in just a moment. Okay. Nuclide symbol. A nuclide symbol is a shorthand way that we can reference an element. For example, we were working with silicon, and in the upper left, so it's not necessarily an exponent or a superscript because we find it to the upper left. That's where we place the mass number. And then to the bottom left, again, I wouldn't necessarily call it a subscript, I guess. This is going to be your atomic number. Now, if you're dealing with an ion, it will show you here. So, if we're dealing with neutral silicon, the mass number that we just went through is 28. I didn't say average atomic mass, just mass number, so it's round to the whole number. And then the bottom left would be 14. Now, what if we were dealing with the -4 anion? Well, the mass number is the same, and the atomic number is the same. Here's where you would show. All right? Now, we just went through chromium +3, and here would be our 52, and, upper left is mass. 52, and then the number, or the atomic number, 24 there. All right, so that's nuclide symbol. We'll come back to this in just a second, because next we need to talk about isotopes. Every element has at least 2 different versions. Okay, so how can they differ? Well, to be the same element, you have to have the same number of protons. So they all have the same number of protons. Well, to be neutral or to be an ion, well, your electrons are going to vary. But what makes one isotope differ from another, one version of an element differ from another version, is the number of neutrons. So they differ in the number of neutrons. There are 3 most common isotopes of hydrogen, actually. You don't have to know this. You just have to know that all elements have at least 2 different versions, and we call them all isotopes. Just like, you and your brother and sister, you're all siblings. All right. Now, one way that we can also refer to the version of element that we're dealing with is the element symbol dash, and this would be the mass number. So there are 3 quote-unquote common isotopes of hydrogen. Now, how would they differ? Well, if they're all different versions of hydrogen, they have to have the same atomic number. So they all have 1 proton. If they're all neutral, they all have 1 electron. So the way that they differ is in their number of neutrons. And I am so sorry. As you can see, this is mass number. Now, you don't necessarily have to have any neutrons. So actually, this version of hydrogen in the nuclei just has a proton. This is called deuterium. We give it a nickname. This is protium, deuterium, and tritium. Don't have to know that. Don't have to know anything specific. We just have to know what isotopes are, how they differ, and that each element has at least 2 different versions. Now, usually, there is one version that is found more often. It has a lot to do with the stability of the nucleus, and that often is revealed in the ratio of protons to neutrons. Well, deuterium, or protium, is found something like 99.8% of the time. And then deuterium about 2.2% of the time, and then we just find tritium in trace amounts of different compounds that contain hydrogen. Now, whenever we are talking about the numbers that we have on the periodic table, they take into account the abundances. These average atomic masses are weighted averages taking into account the percent abundance of your different isotopes. So these average masses represent the average molecule you're going to encounter. If you have a handful of hydrogen atoms, the majority are going to be this version. So that is why the average atomic mass is closer to 1. We'll talk about and show you, and you'll get lots of practice with calculating a weighted average in Chapter 3. All right, so back to the nuclide symbol for a second. So how would one isotope differ from another isotope in the nuclide symbol? Well, the most common form of oxygen is oxygen 16. But we also have oxygen 18, and there's some other isotopes, so we'll just talk about these too. Okay, so how would we deal? We're going to deal with neutral elements. So, all right, both of these are oxygen. So their atomic number must be, 8. Must be 8. Yeah? Now, I'm being told the mass number. The mass number. Now, we're dealing with neutral, so we're not showing any charges. So do we see how one isotope in the nuclide symbol can be written different than the other? It will come through in the different mass number. Now, what if it was oxygen 16 with a -2 charge? Well, protons and neutrons are still the same. Protons are still the same. I would show that there in the upper right. All right. So, just to review some terminology. The types of bonds, remember, are covalent, ionic, and metallic. Do not worry, we will remind ourselves of those to come and learn a lot of great things about these. Now, I bet you reviewed, this is just made of nonmetals, metals and nonmetals, and then just metals, especially with naming. A molecule. We only use the term molecule with things that are covalently bonded. We use the term formula unit with things that are ionically bonded. Okay, structural versus space filling versus ball and stick. So this is just to show us, what we'll see in our book and through different things throughout the year. This is called the structural formula. So what you might create in a Lewis dot structure or applying Vesper theory. This is the ball and stick. And so we're showing bonds with sticks or with a straight just line or a toothpick or something else if we're working with models. Now, in a chemical compound, bonds are not lines or dashes or colored in triangles. They are not toothpicks or kind of plastic. Actually, we know that there's a force of attraction that's created because of the pull of nuclei for electrons. Well, a bonded compound is actually much better represented by a space-filling molecule. So it's really showing, okay, what is the electron cloud like? What about the electron cloud of this central element? I believe this is methane. So carbon and then our hydrogens. So again, structural, space-filling. So that's kind of what we need to really see in our brains eventually, as we're learning throughout the year about compounds, ball and stick. So to show us another example from your book, these all would be space filling. Here would be a ball and stick, and here would be space filling. Okay, so just to address that, that's not, pinnacle, but... Okay, an ion is simply a charged species. And we know that we can have positive ions, those are cations, and negative ions, those are anions. And we know atoms become charged by losing or gaining electrons. Now, a monoatomic ion is a single atom ion. So, for example, fluoride or the calcium ion, where polyatomic ions are made of more than one poly. So, nitrate, hydroxide, ammonium, and it's the entire cluster that we understand has that -1 or that +1 or -3 charge. Where here it's just simply the single element that is carrying this charge. All right, just to refresh on the periodic table, I think, we try to be different, I guess, in chemistry, and we don't call vertical columns, we're calling them family or groups. There are 18 from left to right. Horizontal rows we call periods. And if you want to remember that, a sentence ends in a period, and that's horizontal. There are 7 periods, because remember the lanthanides and actinides belong up in the 6th and then 7th row. All right, we have our staircase that divides metals and nonmetals. We have to make sure that you are just so certain about where do we find metals and nonmetals. And remember where these guys come back up in the table. What are the general properties of metals and nonmetals? What is the distinguishing characteristic of a metal? It is an excellent conductor of heat and electricity. And then other things. They're mainly solids at room temperature pressure. They're usually lustrous and gray, other things, but the distinguishing is the conductivity of electricity and heat. Nonmetals, they are non-conductors or insulators. They're named very appropriately. They are not metals. So a lot of them are gases. They are not shiny. They are brittle instead of being malleable and ductile. And then, of course, we need to just be certain about being able to associate proper charge from where it is on the periodic table. It is also very good to refresh on periodic families. And don't worry, we will revisit this again and again and again. Our alkali metals are column 1 or group 1, not including hydrogen. Alkaline earth, second column. Transition metals are officially the D block, so the sunken region from column 3 through column 12. The halogens are column 17, and the noble gases are column 18. All right, so ladies and gentlemen, that goes through some fundamental concepts that we will work with the rest of the year.